In this lesson, we are going to learn improper integrals. So until now, we have been dealing with definite integrals. However, the integrand inside is a continuous function, and the interval is closed. In this case, we call this type of integral is proper integral. And sometimes we can find integrals of functions where the function or the limits are infinite. In this case, we call this type of integrals improper integral. So there are two cases we are going to deal with. First case, if the interval of the integration is infinite. Here, if you look at the boundaries, there's infinity here. So this type of problem, which we call improper integral, so this is one case because the boundary is infinity. And the second case, even the boundaries is not infinity. See, we didn't see any infinity here. However, this problem, x cannot be 0. So there's we call at x equals 0, there is a singularity here. Similarly to this one, tangent of x is well defined as at power 4 and 2 power 3. However, in this case, x cannot be power 2. Tangent power 2 is not defined. So this type of case 2, we call it singularity at x equals a power 2. So in this case, we are going to have to split the integral into different parts. So today we are going to deal with case 1. For both cases, we are going to solve it in the same way. So let's have a look at case 1. The function being integrated is continuous. There is no singularity for this function. However, in the boundaries, we have infinity as one of the boundaries or two boundaries. So if we have infinity as upper boundary, we are going to write as limit b goes to infinity integration from a to b. We're going to integrate this first and then take the limit. Similarly, if we have the upper boundary as negative infinity, we can also use limit a go to negative infinity. Same thing, integrate this first and do the limit. And if we have both lower and upper boundary as infinity, in this case, we can split this into two. Also, in example 3, I'm going to show you how we are going to solve problems have two boundaries at the infinity. So if the limit exists, then the integral we call the integral converges. Otherwise, we call the integral diverges. So let's have a look at example 1. So if you look at example 1, integration from 0 to infinity e to the negative x dx. E to the negative x exponential function is well defined, is continuous everywhere. But the boundary is infinity, so it's case number 1. So this equals limit. We are going to replace infinity using b. Integration 0 to b e to the negative x dx. So we are going to integrate this first. So it's e to the negative x, negative 0 to b. So this is limit b go to infinity. We solve the integral as same way as before. It's negative e to the negative b minus negative e to the 0, which is limit b go to infinity. Negative 1 over e to the b minus negative 1, so it's plus 1. So as b go to infinity, as we know, b goes to infinity, positive infinity, so this will go to 0. So our final answer, this is 1, because the limit equals a number, so the integral converges to 1. So let's look at example 2. So in example 2, we have to replace also it's continuous, this function. The boundary is infinity here. So limit b goes to infinity, integration 1 to b, 1 minus x e to the negative x dx. So this one you can use integration by tabulus method. So this will be limit b go to infinity. I'm going to solve 1 minus x e to the negative x dx here. So this will be, you can distribute this in e to the negative x minus x e to the negative x dx. Give us negative e to the negative x minus x e to the negative x dx. This one you can use Taylor's method. X e to the negative x, 1, 0. Negative e to the negative x and e to the negative x, positive and negative. So this gives us minus negative x e to the negative x minus e to the negative x. So minus minus plus, so the final answer will be x e to the negative x. So this will be x e to the negative x, 1 to b. So now we can plug the lower and upper boundaries in. So it's b times e to the negative b minus 1 times e to the negative 1. So this will be limit b goes to infinity, b over e to the b minus e to the negative 1. That's a constant. Now we have to deal with this limit here. As b go to infinity, so this is infinity over infinity. We can use L'Hopital's rule. So this will be limit b goes to infinity. We are taking the rule with respect to b, 1 over e to the b minus e to the negative 1. This is a constant. So this one, as b go to infinity, give us 0. So the final answer, negative e to the negative 1. So the integral will converge. So let's have a look at example 3. Integration, sine of x is continuous. So we are going to write this as b goes to infinity, 0 to b, sine of x dx. Limit b goes to infinity, negative cosine of x, 0 to b. This gives us limit b goes to infinity, negative cosine b minus negative cosine 0 give us negative 1. So this will be limit b goes to infinity, negative cosine b plus 1. So this part, as b go to infinity, as we know, this is oscillating. So cosine is between negative 1 to 1. So the limit will be doesn't exist. So the final answer, the integral will diverge. So let's have a look at example 4. Example 4, this is the 1 over x squared plus 1. This function is continuous everywhere, and but the boundaries here is negative infinity, so it's still improper integral. This will be limit a goes to negative infinity, integration a to 4, 1 over 1 plus x squared dx. As we know, that gives us inverse tangent. Inverse x a to 4. So this will be limit x go to a go to negative infinity, tangent inverse 4 minus tangent inverse a. So this is a constant, so we can take it out. Has nothing to do with the limit. Minus limit a go to negative infinity, tangent inverse of a. As we know, tangent inverse gives us an angle between negative power 4 to power 4. So tangent of what? Give you negative infinity. So this value is tangent inverse 4 minus this tangent inverse 4 plus power 2. So it converges. This is the answer key. As we know, e to the x over 1 plus e to the 2x is continuous everywhere, but the boundary is infinity now. So first, we take the antiderivative of the inside. We can use u substitution. So give us tangent of inverse of e to the x. So infinity to positive infinity. I'm not going to use limit, but you could. Okay, so this gives us tangent inverse e to the x, negative infinity, positive infinity. So when we plug negative positive infinity in, tangent e to the infinity give us infinity. So tangent inverse infinity give us power 2. When we plug in negative infinity in, e to negative infinity give us 0. Tangent of what give us 0? Tangent 0. So the final answer is power 2. It converges. Okay, and if you want to write it in a formal way, so this will be limit b goes to infinity, and a goes to negative infinity, a to b e to the x over 1 plus e to the 2x dx. So this gives us tangent inverse e to the x, a to b, and you just put a limit in the front. A go to infinity, negative infinity, b goes to infinity. And then you can do the same thing.